All right. Any questions? Oh, this is fifth one. I have to cover this one as well. Okay. Okay. Spanning set. We know this one. Spanning set is a subspace. All right. We have done that. So if any set in vector space, we then spanning set is a subspace. Yep, we know that. So spanning set is the smallest one. Why is that? Let's try to show that. Smallest one. Spanning set is the smallest one. Let's say W. Alright. So this is set S. W contains set S. And spanning set contains W. Span. So we are going to show this one. The spanning set is the smallest. Let's assume W is the smallest. Let's take any subset, any subspace which is contained by this spanning set, right? All right, let's assume that W contains S. We know that W is a subspace, right? So what can you say about this? Because it is a subspace C1 V1. So here S contains these elements C1 V1. If you consider this linear combination, CK VK, because W is a subspace, this belongs to what? Tell me, because W is a subspace, you know that W is closed under vector addition as well as scalar multiplication. This belongs to W, right? So we know that. So this is a linear combination. This is a linear combination, right? This is a linear combination. Yeah, this is a linear combination. If you consider any linear combination, right? If you consider any linear combination, that one belongs to W. That means span of S subset of W. So are you with me, or are you following me? Or does this make sense? So if you assume W is a subset of spanning set, you can consider any linear combinations of these elements. We know W is a subspace. Because of that, we know that since W is a subspace, we know that this is closed under vector addition and scalar multiplication, right? Therefore, this belongs to W. Therefore, and this one is a subset of W. Therefore, W is same with spanning set. Therefore, spanning set is the smallest subspace of V that contains S. So does this make sense? This proof, 3-line proof, does this make sense to you, or any questions? Tell me your feeling. Just tell me I don't understand or I understood that. Otherwise, I don't know. That's the thing. That's the bad thing about online teaching. Yep. Tell me your opinion. Did you understand this one? This one, spanning set is the, let's draw this one. So this is your V. Okay, let's try to visualize this. This is your vector space. Let's consider two elements. S contains only two vectors, V1, V2, right? So, and now this is your S, right? S. So we know that span, if you consider any linear combination of these two, we get a subspace, right? So we gave a name for that, which is spanning set of S. Span of S. Alright. You cannot find a subspace W which contains S. You cannot find that. So this one is the smallest subspace which contains these 2 points. That's the thing I'm saying. Right? You cannot find any subspace which contains V1 and V2. So this one is the only subspace that contains V1 and V2. This one is the smallest subspace. Right, I hope this makes sense. Okay, and let's, okay, we are ready to talk about linear independent and dependent sets. Okay, this is a set in vector space v1 comma v2 up to vk. There are k number of elements. So this is a subset, right? Not space, and subset. So, but we know that when you consider the all linear combination or spanning set of S, which is a subset of V, and it is the smallest subspace of V which contains S, right? So if you consider this one here, this linear combination is equal to 0 vector, right? So here what do you get? So here you get a system of linear equations. So how do you get that? Let's do example. Here look at this one here. So here this is your R3 is your vector space. R3. R3. This time R vector space, and we know that under standard addition, scale multiplication over the VRR real number set, right? Okay, this is your vector space. So we have 3 vectors in S, right? So determine whether the following vectors, the set of vectors is linear combination, linear independent or linear dependent. Okay, let's find that, right? So definitely you have to consider this one here. Let's consider any combination. Let's consider yep, C1, a combination C1 of V1, yep, C1 times V1 is this one. 1, 2, 3 plus. This is a combination. 1, 2. The second vector 0, 1, 2, and another element in the field are multiplied with this vector v3 minus 3 0 1, and this is equal to the 0 vector. So you can compare coordinates, right? C1 plus minus C3 is equal to 0. Okay? And therefore you can obtain this linear, the system of linear equations. Now we find solutions to this. If you find the solution to this linear system is trivial, so we already, this is a homogeneous system, right? This is a homogeneous system. Homogeneous means the right hand side is equal to 0 vector, right? All right, we already know x 0 vector is a solution to this. If you put, if you plug this one into here, that satisfies. This one satisfies this equation. Therefore, this is a solution to this system. We say this is a trivial solution because we already know. Don't need to solve these things. We already know this one is a solution to this. This is called trivial solution. If this system has only trivial solution, then we say this set is linearly independent. Otherwise, it is linearly dependent. That is the definition. So if this system, this linear system, has only trivial solution, then this set is linearly independent. Otherwise, it is. If that system has non-trivial solutions, has a non-trivial solution, then we say this set is linearly dependent. That's the thing. That's the definition of linearly dependent independent, right? Okay, so how do you find the solution? So all the time try to write this one in terms of matrices. This is your coefficient matrix and this is your right hand side. So you don't need to write right hand side. You know everything on your right hand side is equal to 0, right? Doesn't matter, you can write that, right? This is called augmented matrix. It's all right. So how do you find solutions? You have to reduce this one. If you reduce this, it is easy to find, right? Try to reduce this using row operations. So try to so first consider the first row, and this is the first term, first non-zero term. This is the pivot element. So all elements under this pivot element should be equal to 0. So how do you make this equal to 0? How do you kick this off? How do you kick this off? You have to do a row operation, right? Right? Do those things. You can see this one reduces to this one, right? Here you can. So this is your matrix A. So that means A 0 0 0 1 0 0 0 1 times your C1 C2 C3 is equal to 0 0 0. This means you get trivial solution. C1 is equal to 0, C2 also 0, C3 also. Yep, trivial. So this system has only the trivial solution. Therefore, this set is linearly independent. That's the thing. Right? Let's do another one. Determine this time your vector space is second order polynomials. Right? The vector space is second order polynomial. P2, P2. So set of all second order polynomials, but it is not a vector space. We saw that set of all polynomials, the degree of yeah, less than okay, I understand. This all polynomials, all the degree of each polynomial in this set is less than or equal to 2, right? So that set is a vector space, or I understand that. That this is the notation, right? P2 is not second order polynomial, set of all second order polynomials which its degree less than or equal to 2, right? All right, that set is a vector space. So so P2 is a vector space under polynomial addition and scalar multiplication over, let's say, over the field, let's say real numbers, right? Okay, this is your vector space, and this is a set. This is a subset of this polynomial set, right? There are 3 polynomials in this set. So we are asked to check whether this set is linearly independent or not. Alright, let's check that. Definitely you have to consider this linear combination, right? Okay, expand this and compare the coefficients of each axis, right? So you can compare coefficients both sides here. So try to so equate the constant terms both sides and coefficients of x terms both sides. Then you can obtain linear this system of linear equations, right? So how do you find the solution to this? You have to simplify. Write this one in terms of matrices and simplify. All the time simplify. This is your pivot element. You have to kick the elements under this pivot element. Kick this. You have to get rid of these things. You have to make these things to 0. Do row operations, right? And so this is the reduced one, I think, when you reduce this thing, right? All right. If you look at this one here, so this is the reduced. You can further reduce this one, right? You can kick this one. Yeah, further reduce. Let's kick this term out. So how do you kick that term out? Row 1. Let's do row operation again. I'm doing row operation to row 2, right? So what is my operation? R2 minus R row 1. I subtract row 2 from row 1. Row 2 from row 1. Then this will reduce to this remains the same, and this becomes 0, this becomes 1, this becomes 1 minus 1/3. So okay, this is the reduced one, right? Because this is the pivot element under the under this elements under this pivot element are equal to 0, right? This one also 0 here. So this is your staircase. Okay. Okay, all right. You know these things, right? So, all right. Okay, this is the reduced echelon form, right? And so what we are going to do? Okay. Okay, all right. So here, so this one, this system reduced to this. Okay, now let's solve equations. Very easy to solve. 1, 2, 0, and 0, 1 minus 1/3, 0, 0, 0, and C1, C2, C3. This side's homogeneous, 0, 0, 0. Oh, the last one, C3 can be any value. Okay, and C2 depends on C3. C2 minus 1/3, C3 is equal to 0, and C1 plus 2C2. Okay, C3 can be any value here. There is no restriction for C3. C3 can be any value. Let's put T. Then C2 can be written in terms of T, right? C2 is 1/3 T, and C1 can be written in terms of T. C1 minus 2 minus 2/3 T. All right, this is your solution space. C this is the okay, this is the base of that solution space. C1, C2 1/3, C3 1. Okay, this is the base. T can be any real number. Oh, you get infinitely many solutions. So you don't get trivial solution, you get infinitely many solutions. Therefore, this set is linearly dependent, right? So infinitely many solutions, right? All right, did you understand? I hope you understand well now, right? So far, yeah, go through these examples. I think, yep, the set S is linearly dependent if and only if at least one of it can be written as, yeah, that is trivial, right? So if you have this one, so this is a linear system set, the system of linear equations, right? So this is a homogeneous, yep, homogeneous Ax equals 0. So wait a second. Okay, all right, let's read out this theorem. S is the set, is linearly dependent. That means this system has non-trivial solution. Non-trivial solution. This system has non-trivial solutions. That means for some, yep, this system has non-trivial solutions. That means some CI is not equal to 0. Trivial solutions mean all CI is equal to 0. Non-trivial solution is some CI for some I, CI is not equal to 0. Then you can divide this one by that Ci, one can be written in terms of other vectors. Those are very simple stuff, right? This Vi can be written in terms of other vectors. Other way around is true, right? This one is simple. Yeah. All right. Do you have any questions? I didn't have time to discuss this one. Do you have any questions before discussing this one here? I will give a small break. Yep. Do you have any questions regarding linearly independent, set, linearly dependent, span set? So, okay. Look at this schedule here. So we have covered spanning set and linearly independent, and we are going to talk about basis and dimensions. So we have covered this one, we are going to cover this, hope to cover this one later, and linear transformation, I think, yep. All right, so do you have any questions regarding the previous part? Do you have any questions? Give your feedback. I need your feedback to carry on my work. Otherwise, I cannot continue my work. These are for me. I don't know. Yep. So tell me your opinion. Did you understand the previous part? So shall I continue this one, or do you need time to digest the previous part? What do you want? What do you think? What do you think? Shall I continue this part a little bit? A couple of pages. What do you think? What do you think? I will continue, or will I continue, or I can take another 10 or 15 minutes to cover this part? Or all right. If you okay, then all right. So this one is pretty simple, right? Let's try to understand with uh try to understand this with pictures. All right, all right. This is your vector space. Okay, right. Let's talk about base. Yeah, bases, or bases and dimensions. All right. So this is your vector space. This is your vector space. Very interesting, right? So I hope you are interested in learning these concepts. I don't know, right? Look at this. Oh, this is your vector space. And you can, so here we can find a set. So let's say this is your finite set S, right? S. So you know that spanning set of S is a subspace that which is the smallest subspace that contains S, right? Span of S. If this spanning set is equal to V, we say S generates V, right? S generates V. If these vectors are linearly independent, right, then we give a special name for this set. S is called a basis of V. This is a basis. I think you remember, right? We found many bases earlier, right here. So look at so many bases. There's that. We found many bases. Yeah, this is a basis. This is the base element of W1. So this element generates W1. This is called the base element. If you have a single element, it is a linear independent. Why? So when you consider C1 times 1 comma 0 is equal to 0 0, this implies C1 is 0. You have only trivial solution to this system. If you have a single element in your base set, so this is your base set. So here is another base element. Here is a base element. So we have discussed those things, right? So this is called if V is generated by S or S spans V and S is linearly independent, then S is called a basis for V, a basis. For instance, if you consider this vector space 0, so we know that 0 is a vector space. So the basis for that vector space is the empty set. Empty set is linearly independent set, right? Because it doesn't have anything to prove it is linearly independent or not. That's why this one is linearly independent set. Empty set. It doesn't contain any element, right? It is trivially true, the definition of linearly independent, right? So empty set is a basis for this zero, this vector space 0, right? And if you look at 3 dimensions, R3, right? So this is the base. So any vector in R3 can be written in terms of these 3 vectors. That means I, J, K. Let's denote this is S. S spans R3 and these 3 vectors are linearly independent. You can prove that, right? You can prove that. C1, 1, 0, 0 plus C2, 0, 1, 0 plus C3, 0, 0, 1 is equal to 0, 0. The solution to this system, you get a linear system, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, C1, C2, C2, and this side 0, 0, 0. The solution to this linear system is only the trivial solution. Therefore, this set is linearly independent like that, right? And if you consider Rn vector space, so the number of and this set is the basis. This is the standard basis. This is called standard basis of R3. This is the standard basis. When it comes to R4, this is the standard basis. You can find infinitely many bases, right? You can find infinitely many bases, right? So these are pronounced bases. So if you have E basis, right? Okay. All right. Okay. So same with matrices. If you consider 2 by 2 set of 2 by 2 vectors matrices, so this is the basis. This is the basis of a basis. You can find infinitely many bases, right? This is the base of that vector space. So number of elements in the base set is called dimension of that set of that vector space. So how many base elements? So 1, 2, 3. Then the dimension of this vector space is 3, right? Dimension of this and dimension of this one is n. There are n number of base elements, right? So dimension of this vector space is n. All right. So dimension of this vector space 1, 2, 3, 4. 4. So that means the dimension of this vector space is denoted by dim of vector space V. So here you have 2 by 2. The dimension is 2 times 2, something like that. 4, right? Here look at this. So this set is denoted by all polynomials whose degree is less than or equal to n, right? So we can show. So this is the base. This is the standard basis for this vector space. 1 comma x. From this one, so if you take any polynomial in this space, you can write that polynomial in terms of these these elements 1 comma, yeah, these elements, and these are linearly independent, right? By c1 times 1 plus c2 times x cn times x xn equals 0 times x. So when you compare coefficients both sides, you get a trivial solution. A trivial solution for all life. So trivial solution is the only solution to this system. Therefore, this set is linearly independent and this set spans vector space. This vector space, therefore, this is the base. The number of base element is n plus 1. The dimension of this vector space is n plus 1. All right. So yeah, that's the thing I want to share. Let's do a couple of samples. Let's try to understand this picture, this one here. All right. Do you understand this now? So people who understand this, just raise your hand. Just raise your hand. Who understand this picture here? Can you understand this picture? Right. So let's try to understand this. Okay. do I have space? So right here. Vector space V. Vector space V. You look at this. Let's try to understand it by drawing pictures. This is V, vector space, original space. You have a set S. Okay. Any set, subset S. This is a subset, normal set, right? Contains finite number of vectors. Mhm. So we know that this is the summary of our today's lesson, right? We know that when you span using these vectors, you get spanning set. Right, all right. We showed that this spanning set is a subspace of V, and this set is the smallest subspace which contains S1, right? We know that, right? This is a subspace, and if these two are equal, what happens? These two are equal. We say V is spanned by S1, or S1 spans V, or V is generated by this set S1. Right? If this set is linearly independent, this is called what? Basis. All right. If V is equal to span of S1 and S1 is linearly independent set, is linearly independent set, then this set is called, we give a special name, this set is called basis. The number of elements in the basis is the dimension of that vector space, right? Okay. All right, now you understand this one. Where's that? Yeah, this one. So this is the base. If you have basis, the set of bases is the maximum. The maximum number. This one is the subset of the independent set. So this generate. So can you understand? I think you go and you have to take a piece of paper, sit with a piece of paper, try to understand this picture. So I can visualize this. Now I don't know how to explain this because I have limited time. So try to understand this one here. Generating set this could be linearly independent or not. If this is linearly independent, this could be linearly independent, but the spanning set, when you span using these vectors, it is a subspace. We don't know. This is a subspace. Sometimes it is equal to V, and sometimes the spanning space is equal to V, and this set, if this set S is linearly independent, this set is called basis. All right, basis. Right. I hope you understood that. So I don't know how to explain this because this time I don't get any feeling, any thoughts. to explain this one here. All right. So like that, go sit with a piece of paper and draw diagrams, draw pictures like this. We have vector space, and if you consider a set of vectors, finite set of vectors, or infinite, it could be infinite. The dimension is infinite. Could be infinite, right? Here, if the vector space finite dimensional one, the base element, the base consists of a finite element. So if not, that means the base contains infinitely many elements, right? It is called infinite dimensional space. Those are very simple. So sit with a piece of paper and draw pictures like this. Draw pictures like this. All right. Is this interesting or not? I'm not sure about this. All the time you had to play with little diagrams, then you will understand this subject very well, right? Otherwise you won't understand. All the time try to draw pictures. This is your vector space V, and here you have a set S. When you span this, that means you consider all linear combinations, then you get spanning set. Right. So this is a subspace of V, and this could be linearly independent or dependent. We don't know. We have to check that. This could be linearly dependent or independent. And if this spanning set is equal to V, then yep, then very good, right? We can be written in terms of these vectors. That's why we call V spans. No, V spanned by set S. Very good. That means any element in V can be written in terms of S. Okay, a linear combination of S. Then if this set is linearly independent, or we give a special name. What is that name? That name is basis of V. The number of elements in this base is the dimension of V. Okay, that's the small story, right? Try to draw pictures if you don't understand. We talked about two spaces. Draw pictures all the time. V, W1, W2. Intersection is always a subspace of V, but the union does not need to be a subspace. But if you define W1 plus W2 in that way, I think you remember, right? So this is a subspace containing W1 and W2. This would be the smallest subspace containing W1 and W2, right? Something like that. And I recommend you to sit with paper and draw diagrams like that. Imagine, visualize these. Then this would be pretty easy, right? All right. I will end my session, today's session.